Yesterday we jumped forward a little bit and analyzed problems involving multiple forces, but involving multiple forces with funny angles. Here, we know how to analyze multiple force problems. We know how to analyze funny angles. We just got to kind of combine those two things together. Here's an object, wagon, box, whatever it is, car, doesn't matter what it is. It's being pulled to the right with a force of 100 newtons. We'll call that FA, the force applied. Call it F1, call it whatever you want. There's an angle of 30 degrees with the horizontal. There's a force of friction that's pulling it back. We're going to make the force of friction 20 newtons. We got another person pulling it back as well. That person, we'll call it FP, the force of the person, of 30 newtons. The mass of this object, whatever it is 20 kilograms. We want to find the acceleration of this object. We'll do this one together, and then we'll take a look at the homework that we had last night, a couple questions of homework, see where you did on that. So what do? Well, we know that there's a couple of things that we can do here. We know how to deal with multiple force problems. We draw a free body diagram. We've already got that free body diagram. Then we'd like to say the net force is equal to the sum of the forces, but we've got a little bit of an issue before we say that. We've got a funny angle, but that's okay, because we know how to deal with funny angles as well. Let's take it off to the side, put it out of its misery here, and find the x and y components of that 100 newtons. Here's x, here's y. Well, let's say cosine 30 degrees is equal to x over 100, the adjacent side over the hypotenuse. X is going to be equal to 86.6 newtons. Let's say sine 30 degrees is equal to y, the opposite side over the hypotenuse. Y ends up being equal to 50 newtons. There we go. It's gone. We never have to deal with that 100 Newton force again. I can, if I want to, erase that 100 newtons and replace it with my two forces. My 86.6 newtons, we'll call it FAX and FAY. My 86.6 and my 50 newtons. I don't have to redraw that diagram if I don't want to, but for some of us it's useful, it's helpful to do that. Whatever you want to do there. Now it looks like I've only got one force that's on the vertical axis. That doesn't seem to help me too much because although I've gotten rid of my funny angles, I've still got forces in two dimensions. Right? I can't say F net is equal to the sum of the forces, F1 plus F2 or whatever we got, if I have forces in two dimensions. Do I have forces in two dimensions here? Do I have both an x and a y component? Well, remember what we said at the very beginning of the lesson, the first day that we looked at multiple forces. If you get forces that cancel each other, then cancel them. Well, if we draw all the forces acting on this object, we'll see that we have a force of gravity acting down. We have a normal force acting up on this. And if we combine this with this and this, they cancel. The two upward forces here, the normal force and gravity combined, normal force and the y component of FA combined cancel out or balance the gravitational force. So what am I left with? As far as unbalanced forces go, I'm left with FP, FF, and FA, x component. Now we can do this the way we've been doing problems for the last few weeks. Let's say the net force is equal to the sum of the forces. FP plus FF plus F applied x component. 20 times the acceleration equals negative 30 plus negative 20 plus 50. Plus 86.6. So what do we get here? 36.6 divided by 20. I think it was 1.8 meters per second squared. Rosie, did I make a mistake? No. 1.8 meters per second squared. We went through that big challenging question yesterday that I said, you're never going to see a question like this on an exam. But we went through it for two reasons, right? We talked about this yesterday. One, because doing hard questions makes you smarter. But two, because it was the perfect question to illustrate that even when you don't know exactly how to do something, if you can see big picture, but also compartmentalize the question into little bits that you know, sometimes you can do it. Hey, this is one of those questions just a lot easier than that question we saw yesterday. Okay, this is two questions. This is a funny angle question that we know how to deal with. This is a F net is equal to the sum of the forces question that we know how to deal with. So do those things. Yeah, that doesn't mean you're going to get the right answer to a question. Sometimes we still make a mistake, but it does mean that everybody, for almost every single question, is going to have somewhere to go, somewhere to start. Okay, there should never really be a question where we don't have any idea. Okay, even one of these questions that's a little bit different, we still have an idea as to where to go, right? Funny angle and F net is equal to the sum of the forces. All right. Yesterday, I left you with two questions for homework. It was questions 16 and 17 on your worksheet. For question 16, I got an acceleration for 16 of 2.6 meters per second squared. And for question 17, I get an acceleration of 1.1 meters per second squared. Anybody want to go over one or both of those questions? No, you guys are good with them? All right. If you guys think you're so smart then, let's try one more question that's going to throw a little bit of a twist into this, okay? Here's the box. We're going to pull it. We're going to say its mass is 20 kilograms again. We're going to pull it with a force here that we'll call FA. Well, let's make it 100 newtons again. It makes the math easy. Let's make our angle 30 degrees. So far, exactly the same as the last one that I did with you. But this time, instead of giving you a force of friction that's going to act to the left to oppose the applied force, I'm going to give you a coefficient of kinetic friction. The coefficient of kinetic friction is going to be 0.20. So we don't have to figure out whether this thing moves or not. See if it overcomes static friction. I'm telling you right now, it moves. Okay, it moves. There's going to be kinetic friction. What's the acceleration of this system if the coefficient of kinetic friction is 0.20? Everybody have a look up at the front now. So what do you see here? We see a question that's very much like the question that we did a few minutes ago, but there's a little bit of a twist in that we have a coefficient of friction here. That's okay. We can still do some things that we know how to do, like, for instance, deal with the funny angle. Let's take the funny angle off to the side and deal with it. We got an angle of 30 degrees over here. We got a force of 100 newtons. This is X. This is Y. We're going to say the X component is 86.6. That comes from the cosine function. And the Y component is 50 newtons. That comes from the sine function. Now, I like to erase this and replace it with those two vectors. You don't have to, but that's what I like to do. So 86.6, I'm going to call that Fx. And I'm going to say Fy is 50 newtons. What other forces do I have acting here? Well, of course, I've got friction acting back this way. I don't know what its value is. Okay, but I know that it acts backwards. It's going to counter the motion of this box or whatever it is. We also know that I have a force of gravity acting down and a normal force acting up. What do we know about the value of the normal force compared to the force of gravity? Same value? It's going to be smaller, right? We don't know exactly how much smaller right now, but we know it's going to be smaller because we know in this case that the Y component of the applied force is helping the normal force, right? It's in static equilibrium vertically, which means that it doesn't move up or down vertically, which means that all the vertical forces have to balance. Fg acting downwards has to balance Fn and Fy acting upwards. Now, in order to find the force of friction here, I need the normal force. Lots of people, as I was walking around, I saw lots of people say the normal force is m times g. No, it isn't. Okay, if Fn balanced force of gravity, then the normal force would be m times g. But it doesn't balance it here. Combined with the y component, it balances it here. Does anybody want to make a suggestion as to how I might find the value of the normal force here so that I can plug it into the force of friction equation? Yeah, Rosie? Yes. Let's work out Fg and then minus 50 newtons from it. So let's go off to the side here just so we don't make it too cluttered in the middle. Let's say the force of gravity, 20 times 9.81, that's the downward force, has to equal the upward forces, Fn plus 50 newtons. 20 times 9.81 is 196.2. We take the 50 over by subtracting and we get Fn is 146.2 newtons. So it's not 196.2 newtons, m times g, it's 146.2. It's 50 newtons less than gravity because the y component of the applied force helps it out. So now let's say mu 0.20 times the normal force of 146.2 newtons gives me a value of 29 point, is that right? 29.24 newtons. That's my force of friction, okay, as opposed to 0.2 times 196.2, which would have been, what, 38 point something for my force of friction, which is what a lot of you would have gotten. All right, we got a lot of stuff going on here. Now let's choose another color just to separate it here. Let's say F net is equal to the sum of the forces. Hey, why am I getting rid of those? Because they cancel, right? All three of them combined cancel. The net force is equal to whatever we have left on the x-axis, which is FF plus FX. We're going to say 20 times the acceleration equals negative 29.24 newtons plus 86.6 newtons. We get 2.9 meters per second squared. Agree with that? Yeah? How many people got that? Good. Excellent. That's a tough question, eh? But I'll tell you what. We can work through it logically and figure it out, right? We know to do this. We know to do this. We know that we've got to find the force of friction here. Lots of you found it wrong because you calculated the normal force wrong. Hey, I can live with that. Okay, I'd like you to get 100% on this question, but if you make a mistake with the normal force, you're still going to get good marks on this question, right? All of us are capable of getting a 4 to 5 on this question. All of us are. Okay? Some of you, the ones that are really good at thinking here, might be capable of getting a 5 out of 5 because you recognize this whole deal with the normal force here is 146. Okay? But all of us can recognize this and the fact that we've got to find the force of friction and get at least a 4 to 5. Okay? All right. I got another one for you. This one's even different still. 3.2, and I don't have the page number there. I'm not sure what page that is. You'll figure it out. Two people, A and B, are dragging a canoe out of a lake onto a, sorry, this is not the one that I wanted to do, sorry. 3.3 on 133 is the one I wanted to do. The reason I had this here is because 3.3 refers to 3.2 here. So we're doing this question, but we're going to have to refer back to the previous question for some numbers. We've already done that other one, 3.2, a while ago. Sorry. So we're referring to example 3.2 on page 132. Person A thinks that if A and B each pull on a rope forming an angle of 20 degrees with the bow, the net force on the canoe will be greater than in example 3.2. Well, let's see what we had in 3.2 real quickly here. They're both pulling with a force of 60 newtons. There was a force of friction of 85 newtons backwards. The net force in this question ended up being equal to 35 newtons. So we want to see in 3.3, if we're pulling at angles of 20 degrees, if we can make a bigger net force here. So let's draw the free body diagram here. We got a force going this way, force going this way, both 60 newtons. And we had a force of friction of, what, 85 newtons backwards? Let's make a prediction first before we actually solve this. Okay, the question says, is person A's thinking correct? Is the net force here going to be bigger than the net force was in the last question? In other words, is the net force going to be bigger than 35 newtons? Who says yes, it will be bigger? Who says the net force will be bigger? Okay. Who says no, the net force will be smaller? Okay, we've got a couple of people saying yes, a few more people saying no, and there's lots of people that aren't sure whether it's going to be bigger or smaller. That's okay. I know what my prediction is right now, but I'm not going to give it to you until after the fact. Okay, that's the way, by the way, you always get your prediction right, is giving your prediction after the fact, right? Pretty sure I know what the answer is going to be here. I don't know what the net force is going to be off the top of my head, but I'm pretty sure I know the net force, whether it's going to be bigger or smaller, and I'll explain why after we're through this here. Okay, what do you want to do first? This is looking at it from above, right? This is not one of those problems where, you know, we're pulling a wagon, looking at it from the side. This has got two funny angles. We got to get rid of those funny angles. So let's do that now. Let's say if this is 60 newtons and this is 20 degrees, this would be my x, this would be my y. Cosine 20 degrees is equal to x over 60. What's x equal to? 60 cos 20, 56.38 newtons for my x component. Thanks for not giving up, Fraser. Sine 20 degrees is equal to the y-axis, that's the opposite side, over 60 newtons. Y is going to end up being equal to, get that one? 20.5 newtons, thank you. Now, technically, I got to do the other one as well, right? But what do you notice about the other one? It's the same numbers, right? Should I go through this process again? I mean, certainly if you want to, go ahead, but I don't need to. I'm going to replace this one with 56.38 newtons. We'll call this F1x, 56.38 newtons. And F1y was 20.5 newtons. Now let's replace the other one because it's the same angle and the same force. F2x, 56.38 newtons. And F2y, boy, it's getting cluttered here, 20.5 newtons. Now, there is a force of gravity and a normal force acting on this, but remember, looking at it from above, we're not moving it up or down. We're pulling everything horizontally, so the normal force and gravity cancel out here. What else cancels out here? Our y components, right? That leaves me with three forces all on the same axis. My net force is equal to FF plus F1x plus F2x. Now I'm just looking for the net force here, so I'm going to say FF is negative 85, F1x is 56.38, and F2x is 56.38. What do we get when we add those up? 27.8 newtons there. My net force was 35. My net force is now 27.8. Hey, some of you made the wrong prediction. That's okay. Okay, that's okay. We make predictions wrong all the time. But some of you made the right prediction. Hey, I was going to predict that it was going to be a smaller force. In fact, I knew it was going to be a smaller force. It wasn't really much of a prediction. Why did I know it was going to be a smaller force? Well, think of it this way. If in this question, 3.2, I was pulling it with 60 newtons twice, but all of that force, all of that 120 Newton force was contributing to its horizontal motion. In this question, we're pulling with two 60 Newton forces again, but only part of the 60 newtons was contributing to the horizontal motion. Well, then the net force is going to be bigger when all of the force is contributing to its horizontal motion, right? When all of its 60 newtons is contributing to the net force. Does that make sense? It's different than the last question, right? Quite a bit different than the last question, but yet real similar to the last question as well. Okay? Get rid of the funny angles. Okay? And if things cancel out, then F net is equal to the sum of the forces. All right, take a look at these two questions, please, on page 134. I'll let you work on those individually. Let's take a look at number one. Suppose person A pulls a rope forming an angle of 40 degrees with the bow, and B pulls rope forming an angle of 20 degrees with the bow. Each person applies a force of 60 newtons on the rope. The canoe and the ropes are parallel to the surface of the beach. The canoe is being dragged across a frictionless surface. Calculate the net force on the canoe. Here's the canoe. Looking at it from above, we have a force of 60 newtons at 40 degrees. I'm going to call that FA. And I'm pulling FB, also with a force of 60 newtons at an angle of 20 degrees. Okay, what do you see here? First of all, you see a problem with multiple forces, free body diagram. Well, we've got our free body diagram drawn already, right? We also see a problem with funny angles. Let's get rid of the funny angles. There's two of them we have to get rid of this time. Unlike the last question, because they're at different angles, we can't just do it once and take the data from that one and apply it to the other one. So let's go down here and say, look, we got 60 newtons at 40 degrees. Does anybody have what the value of X is there? Value of Y? Just to save a little bit of time here. All right, we're using the cosine function for X and the sine function for Y, but what does the answer work out to be there for X? What does he get that? 56.38, thank you. 46, okay. 46.0, okay, thank you. And now the Y component is going to be, you get that one? 38.57, thank you. All right, there's one of them. We can replace this now with the X and the Y if we want. Let's call this FAX, FAY. FAX is 46 newtons. FAY is 38.57 newtons. Okay, good. Let's do the Y component now. Sorry, the second vector, I mean, the X and Y components of the second vector. Here's 20 degrees. Here's X, here's Y, 60 newtons. We're going to say cosine 20 degrees is equal to X over 60. What do we end up getting for this one? Miles, you get that one? 56.38. Oh, that's the one you were giving me last one, 56.38. Thank you. And Miles, you get Y component as well? 20.52. Okay, let's replace this with those two vectors. We'll say FBX 56.38, FBY is 20.52. Okay, it's looking better now. That's some bad news, though. What's the bad news? No? Oh, your hand was up there. No? Oh, yeah. Forces don't cancel, right? We got 46 and 56 both to the right. Clearly, they don't cancel. Then we got 20.52 down and 38.57 up. They don't cancel either. Uh-oh. What are we going to do? You've never done a question like this before. What are we going to do? We gave you this question because we believe that you can work through this, right? We think you can work through this. With what you've learned, we think you can figure this out on your own. And I'm curious if anybody did. When we were adding vectors together with velocity and displacement, do you remember we did this? We would have said 46 for the x component of the first one and 38.57 for the y component of the first one. 56.38 for the second one for the x and negative 20.52. Why can I not just say F net is equal to the sum of the forces? Why can I not just say F net is equal to 46 plus 56 here? Well, because it's not just on one axis. I'm still adding the forces together, right? Really what I'm saying here is F net for the x component is equal to 46 plus 56. F net for the y component is 38 plus negative 20. But I got to do it on both axes because my forces on the y-axis for the first time didn't cancel. That one, what do you get for the x component? 46 plus 56.38. 112.38. Try the y component there now. 38.57 plus negative 20.52. Now what? Yeah, go ahead. Sorry, say it again. $102? Oh, yeah, you're right. Thank you. Yeah, thank you. Now what? Oh, you guys know what to do here now. Seriously. Even though we haven't done a question like this, at least in this context, you know exactly what to do here. I got a vector in the x-axis. I got a vector on the y-axis. I want to combine those vectors. I want to add these vectors together. I'm not going to say 102 plus 18 is going to give me 120 because that's adding them together as scalars. I got to add them together as vectors, and you know how to do that. 102.38 to the right, 18.05 up. How many people did that? How many people set it up like that? My resultant vector is right here. My angle is right here. We're going to say R is equal to 102.38 squared plus 18.05 squared. Square root that. Nick and this side of the room is going to calculate the value of R. This side of the room is going to calculate the value of theta. It's the inverse tan function of opposite over adjacent. And 6, thank you. 103.96 for this one. We're going to round that to, how many digits should it be? I think 3 digits, yeah. So 104 newtons. And theta works out to be, what's theta work out to be there? Sorry, 10 degrees, 10.0, 9.998. So we would make it 10.0, yeah. And that would be, what, 10.0 degrees north of east. So lots of you guys had a little bit of trouble with it. That's okay. That's okay. But take a step back from it for a second and look at why I have confidence in you, more confidence in you than you have in you, that you can solve questions like this. Okay, what does it boil down to? Things that we've done. Okay, and that's what I want you to realize. Just do things that you know. Okay, got funny angles, get rid of them. Hey, if you can cancel things out, great. Okay, like we did over here in the example. Cancel it with the y components, that's great. Can't cancel it out, that's okay. If you can't cancel it out, deal with it. Okay, deal with it like you did for displacement vectors and velocity vectors back in Unit 1. Add up the x's, add up the y's, combine them. But combine them vectorially, right? Okay, let's keep working on question number 2. And then I'll give you another question in a few minutes after you've done that one. So look at question number 2 now. It says 2 people A and B are dragging a sled on a horizontal icy surface with 2 light ropes. Person A applies a force of 65 newtons at 30 degrees. Now, this is a notation that's a little bit odd. We don't use this notation on tests. We don't use this notation in Physics 30. It's a notation that your textbook uses for angles. I'm not a big fan of it, but it is what it is. Okay, we'll go with it for this question. Person A is pulling at 30 degrees, which means this way. FA is 30 degrees above that horizontal, and its value is 65.0 newtons. Now the second one, person B is pulling at 70 newtons at 300 degrees. 300 degrees, if you think about this, if this is 30 degrees, then 300 degrees would keep going around here like this, and it would be 60 degrees short of making it all the way around, right? 360 degrees in a circle. So if we go 30 degrees, okay, keep going around, keep going around, keep going around, stop 60 degrees short of a full circle. So in other words, that second vector is going to be down here. Going to make that FB 70 newtons, and it's 60 degrees just short of completing the circle all the way around there. That's what my diagram looks like. Listen, I don't want you to lose any sleep over the notation that they use for the angles here. If I gave you this question on a test or on a quiz or on an exam or whatever, then I would give you the angles as I've given them to you in the diagram. So don't panic about that if you didn't quite follow what I just did there. All right, there is no force of friction. The ropes are parallel to the icy surface. What's the net force on the sled? We get 2 funny angles that we got to get rid of. I'm actually going to get rid of this, so I got a little bit more space to work there. So let's get rid of those 2 funny angles over there now. Let's say we've got a 65 Newton force right here at an angle of 30 degrees. This is X, this is Y. Question down there? No, it's good. What does X work out to be there? Cosine 30 degrees is equal to X over 65. Ben, you got that? (56.29 newtons). Is that right, guys? Okay, thank you. Ben, you got the Y component there for that as well? Sine 30, actually that one's easier. Sine 30 is equal to Y over 65, 32.5. All right, let's replace it. Let's get rid of that and draw in 56.29 and 32.5. Good. Let's do the other one now. Here we've got 60 degrees right here. This is X, this is Y, 70 newtons. Cosine 60 degrees is equal to X over 70. What are we going to get for that one? You have that one? 35 newtons, thank you. And the Y component, is going to be sine 60 degrees equal to y over 70, which is 60.6. Thank you. All right, let's replace those now. Again, you don't have to redraw it like this, but I don't know. I think it's helpful, and I know in my experience, it tends to work well for lots of students, not necessarily everybody, but lots of students. We're going to say 35 newtons this way, and we're going to say 60.6 newtons this way. Does anything cancel? Anything balance each other? Because if they do, you should get rid of them. It sure would be nice if they did. And that way we could make it a one-dimensional problem. Problem is they don't. So let's break it into x's and y's. 56.29 for the x component of the first one, 32.5 for the y component. 35 and, Sonia, what's the y component of the second one? Oh, I'm asking you because I know you know negative, right? 60.6 newtons. Good. Negative because it's downwards, right? Good. What does that give me? 91.29. And what does that one give me? And now we just combine them the way we've combined them a million times before with in other contexts. 91.29, 28.1. What does R work out to be there, doing the Pythagorean theorem? Get that, Emma? 95.4. Okay, thank you. And theta works out to be what? We'll leave it at that. Okay, they give me a notation that's consistent with the notation they gave me in the question. But if you can calculate that angle of 16.9, that's good enough. That's good enough for us. All right. Okay, I got one more question for you. If you want to just snap a photo of this, you can. It's not in your textbook. So either write it out or snap a picture of it. And then do this one. We got 3 forces, only one funny angle. That's good. But a little bit more work to do in the other area because there's 3 forces.